Physics is all about understanding the fundamental rules of the universe and predicting how it behaves. So understanding what makes up everything in it is quite important. You probably know that tiny atoms make up all matter in the universe, but even smaller building blocks of the universe exist, which are generally called particles. So what is a particle like? You might think that a particle is like a super tiny version of this ball, but it's not. This ball must have one certain position and speed at any point in time, right? But believe it or not, all matter, including both this macroscopic ball and a microscopic particle, can behave like waves.
This is so strange because these waves are actually probability waves, called wave functions, that determine the probabilities that the matter would have a specific value of a physical property like position at any point in time. The probabilities themselves depend on the height of the wave function, or the amplitude. This also means that the matter does not have just one position. Instead, the wave function is in multiple places at once, so occupies multiple positions at the same time. After all, it's just like any other wave, say a light wave. It can move through two slits simultaneously to form constructive and destructive interference patterns, just like my laser's light waves do with a double slit. So if my laser's light waves were wave functions, when measured, these areas would show high probabilities and these low probabilities.
Now don't sciencey talk freak you out. Wave functions can be like this, or this, but they all just give one probability for each value of a physical property. Just be careful, the matter is not physically its wave function. Wave functions only describe all possible knowledge of it. So why can't you see large stuff like this ball behaving like waves in multiple places at once? Because of the Broad equation. Oh come on, more math and sciencey talk? Welcome to quantum physics. But to simplify this, if we just look at mass and wavelengths, as the mass increases, the wavelength decreases. So a large mass means very small wavelengths that's actually undetectable, while a very small mass means a relatively large wavelength that is detectable. This means that only smaller masses have detectable wave-like behavior. In addition to strange wave-like behavior, the physical properties of particles are what is called quantized instead of continuous. Here's an analogy. If we take a string and cut it up into smaller and smaller pieces, continuous means that you can go on cutting forever. But quantized means that there's a limit to how small you can possibly go. That small limit, called the quantum, is so incredibly small that everything looks continuous to us, but it does matter with particles. So properties of particles are like tiny ladders where their values can move up and down only on the runs, and never in between runs. Although our current model of particles very accurately describes a very small, it still isn't perfect or complete. A big hole is its inability to incorporate gravity despite many unsuccessful efforts. More work still needs to be done to revise or even rebuild our model of the universe, and this task could be up to you.